All right. Good morning, everyone. So let's start. Do you have any questions? Okay. So where did we leave off last time? So give me a moment here. So last time, we were discussing the Neyman-Pearson lemma. Right, and the content of the Neyman-Pearson lemma is this: if you have two simple hypotheses, all right, and you have a, let's say you have a critical region. Now, the feature of this critical region is that it involves some test step, right? You know, I mean, so, right, for example, X bar bigger than K or something like that, right? That's, but do notice, right, that exactly the point is our critical region is formed through some statistic, right, that we were familiar with, some intuitive statistic. And, you know, most likely is some kind of estimator for data, right? So we want to show, right, goal is to show that C is the most powerful. So Neyman-Pearson says this, right? Neyman-Pearson says that, well, go ahead and check that, right? Somehow that the likelihood ratio, which is the likelihood under the norm divided by the likelihood under the alternative, will be less than or equal to K in C, right? And bigger than K, little k, right, in C complement. And if that is true, then your critical region C will be the most powerful, okay? Will be the most powerful of size alpha. All right, so yeah, I mean, so notation wise, right? This right here, I always use to denote the sample, right? So X will denote the realization of the sample values, right? So that's there to highlight that, of course, the likelihood function is computed, right, through the sample values, for example, or any statistics is computed through the sample values. Is that okay? Like this. All right, so, right, so actually, you know, this notation in C and out of C, that kind of thing, is really, right, all in all, it's trying to say that basically the likelihood ratio, right, less than or equal to K, is exactly equivalent to the region C, right? And the likelihood ratio bigger than K is equal to C complement, okay? And basically, the name of the game is somehow to transform, right, through working with the likelihood ratio to show that this region somehow becomes the critical region that you propose. And finally, right, I mean, the point is that to check that somehow the likelihood ratio is really a function of the test stat that that we're concerned with. Okay. All right. So we were in the middle of considering the example last time like this: x1 up to xn IID. This time we're playing with the population variance. Okay, sigma square unknown. So our proposed region, right, is that, oh, sorry, let's put down the hypothesis. The hypothesis, let's say abstractly like this. And, you know, let's say that sigma 1 square is less than sigma 0 square, all right? So the hypothesis says that the alternative is the true population variance, right? In the alternative is less than the, you know, you can think of this as 1 and this is 4, for example, right? All right. So our proposed critical region is clearly S square is small enough, right? S square is small enough. By the way, right, I mean, let's get back to the basic in case you feel a lot of these are too abstract. I mean, a warm-up question, decide K so that C has size alpha. Okay, how do we do this? This is not Neyman Pearson, all right? This is just a warm-up question so that we kind of get to the mood of the problem. But how will we do this? So you see, right, that exactly the formulation is alpha is probability of C under the norm, which is the probability that S squared less than or equal to K, and the true population variance is sigma naught. Okay. Now what do we do here? We use a sampling distribution of S squared, right? So S squared n minus 1 S squared, right, over sigma squared. Correct. Like this. Right, where we plug in the sigma 0 because that's the quote, right, proposed or true the population variance under the norm. And then obviously then, right, this will be a chi-square n minus 1. Whoops, what am I doing, right? I need to also do the same thing for k, n minus 1 k over sigma 0 square. And then, right, clearly we get n minus 1k over sigma 0 square is chi-square n minus 1 alpha. And from there, right, we get okay. Is that okay? All right, so that's just, you know, kind of grounding us to what the problem is. We kind of, you know, assume that K can be found, right? Big K can be found, that's no problem. The issue is really to, right, check whether C is the most powerful. So what do we do here? Well, so the steps, right, is that first we form the likelihood ratio. Likelihood ratio will be, right, so this is normal 0 sigma square, right? So under the null, it's going to be 1 over square root of 2 pi sigma 0 square raised to the n over 2. Then e of minus 1/2 sum of xi square over 2 sigma no square divided by 1 over square root of 2 pi sigma 1 square raised to n over 2, square root extends over here, times minus 1/2 sum xi square divided by, oh, sorry. If I have a 2 there, then I don't need this. Divided by sigma 1 square. Okay. All right, so what's our goal? Because the critical region is that s squared is less than or equal to k. All right, or our test stat is s squared. The goal is to somehow show that the likelihood ratio is dependent on s squared. Is that okay? So basically, the goal is somehow to make s squared show up in this expression, right? So how can we do that? Again, remember that besides, like, roughly speaking, right, besides the sample, the other constants can be ignored because they don't play a role in the dependence of the likelihood ratio onto the test stat. So in other words, right, this can be ignored, this can be ignored. The exponential we can pull together. So the point is, right, the expression we want to pay attention to is sum of xi square over sigma 1 square minus sum of xi square over sigma 0 square. This is what we want to pay attention to. Okay. So let me ask you this. How is it possible that there's something s squared show up here? How is it possible that something like s squared show up through this expression? So maybe let me remind you, right, of a similar problem and to show you how things can work. The other problem that we looked at last time was this, right? x1 up to xn IID normal mu1. So mu here is unknown. The null is mu equals to mu naught. The alternative is mu equals to mu1. Let's say mu1 bigger than mu naught. Then our rejection region is x bar bigger than or equal to k. To check that this is the most powerful, we again form the likelihood ratio. But this time, because, right, sigma square equal on both sides, it will be e to a minus 1/2, right, sum of xi minus mu0 square divided by e to minus 1/2 sum of xi minus mu1 square. Yeah, I'll get back to you, Alice. Something like that, right? 1 second. So here, right, you see again, the goal is to play with this expression, which is sum of xi minus mu1 square minus sum of xi minus mu0 square. And, right, somehow make x bar show up. But because, right, this is the critical region involves x bar. But you see, this is quite easy because, you know, this sum of xi cancel, xi square cancel, right? So we end up having 2 mu naught minus mu1 times nx bar as the expression, right? Well, with that caveat of mu1 square minus mu0 square, which we don't care for, right? You remember? So that's how, right, x bar show up through this expression. But again, we want x bar to show up because our critical region involves x bar. Here, right, the test is about the variance. So the critical region involves s squared. So, right, the likelihood ratio now should somehow make s squared show up. Is that okay? So before we even go to the technical detail, is the goal clear? Do you understand what I'm trying to do here? Any question on this? Right, make sure you can follow the story, right? The idea that the technical details precise, right? All I'm trying to do here is reduce the likelihood ratio to somehow a dependence on s squared. Okay, same as this story here, but here, right, because I'm playing with x bar, I try to reduce the likelihood ratio to a dependence on x bar. Because the test here is on the sample on the population mean, the test here is on the population variance. Okay. All right. So if there's no question, let's consider Alice's proposal. You say the top is, so you mean here, this is s squared times n minus 1. Is that what you're saying? Right, except that's not quite right, right? Because so now this is a neutral, right? Let's separate it out. Let's go back to the expression. So we have sum of xi squared over sigma 1 squared minus sum of xi squared over sigma 2 squared. Now, s squared will be sum of xi minus x bar squared over n minus 1. That's the definition of s squared, right? So s squared times n minus 1 will be this, right? So it's not quite this. Is that okay? So, right, it seems like it, but precisely this is the expression. Is that okay? So in other words, actually to make s squared show up, so you're not quite far from it, but to make s squared show up, what do we need? We need that identity that we used, long time ago. The identity was sum of xi minus mu square is sum of xi minus x bar square plus n x bar minus mu square. Remember this? So what's mu in this case? What's our mu in this case? Mu is 0, correct. So you see, we have that sum of xi squared, right, is, and let me throw in, right, 1 over n minus 1 here, because that's our goal, is equal to s squared plus n over n minus 1 x bar squared. Are you okay? Are we okay? So in other words, right, this guy right here, right, this guy right here will be substituted as n minus 1 s squared, right, plus n x bar squared divided by sigma 1 squared minus n minus 1 s squared plus n x bar squared divided by sigma 2 squared. Oh, what am I saying, right? I use sigma 0 and sigma 1, right? Is that okay? Does anyone have any question at this point about what's going on? So again, right, because this expression came from, oh, did I switch things again? Sorry. Doesn't matter. But yeah. Yeah. So right here, right, Christine, this is the identity that we talked about a while ago when we discussed s squared. So if you divide everything, because mu equal to 0, right, you don't have this. If you divide everything by n minus 1, then this s squared shows up. All right. Now, in this expression that I care for, it only has the sum without the n minus 1. So I multiply everything by n minus 1 on this side to get the sum is equal to n minus 1 plus nx bar. Is that okay? So basically this, right, is just that. Do you follow? Yeah, so I do it twice. So, right, I mean, again, right, I want to make s squared show up somehow. Right, but you know, the division by n minus 1 is to make s squared show up, because that's the definition of s squared. Is that okay? It's sort of like artificial, but that's the first division is to make s squared show up. But the second is because I don't need that on this side for this expression, right? So yeah, that I might seem to be doing something useless, but this is to make s squared show up. And then I discovered that I don't need it, so I just turn it back, but I still keep s squared. Is that okay? But after I answer your question. All right. So again, right, let's not lose track of what we're after. What we're after is, again, this is our likelihood ratio. And we discover, right, that the essential dependence on the sample is through this expression. And we want to connect this expression to s squared. Okay. So that's something like that. All right, so let's get back to the likelihood ratio business. So the likelihood ratio then is going to be a constant, right? And then exponential of, let's say this, right? N minus 1 1 over sigma 1 square minus 1 over sigma 0 square times s square plus n times 1 over sigma 1 square minus 1 over sigma 0 square times x bar square. Are we okay? Right, because this is just the exponential. The c is these guys right here, right? The c is that guys right here, which are non-essential. All right. So our rejection region is s squared less than or equal to k, right? Because we have sigma 1 square is less than or equal to sigma 0 square. So, I mean, if we follow our kind of cheating whatever assumption, then we need to show what? We need to show that the likelihood ratio function is what kind of function of s squared. Because, right, we reject if likelihood ratio less than or equal to k, right? So what is the usual kind of crux move here? We want to show the likelihood ratio is what? Decreasing? Monotone. Fine, but monotone in what direction? Increasing, right? Increasing, because you see, are we okay? Increasing, right? Increasing. Is that okay? That's the usual. I mean, you know, it's quite easy to tell, right? If this is this, then that would be a decreasing, right? But if it's this, then it's increasing, right? All right. So that's what we want. Do we have it? Do we have it through this expression? Are we done? Do we have it? Why? Why do we have it? Yeah, can you elaborate a little more? So you probably think of something like this. And then that means that this is positive. So that means this is an increasing function. Is that what you're thinking? That's fine. No, I mean, there's no messing up here, right? That's what you're saying. Except here is very subtle. It's not quite. Does anyone see why it's not quite? So basically what I'm saying, right? If S squared increase, then LR must increase, likelihood ratio must increase. If S squared decrease, then likelihood ratio must decrease. Is that clear? Is that the case? Through this expression? If you think it's clear, just maybe say it. Why not, Christine? Why don't you think that is the case? Okay, so let me point out, right? When S squared changed, does X bar change? Or let me put it this way, right? When the sample changed, does X bar change? Well, definitely yes, right? So if the sample changes, then X bar changes, right? So if S squared changes through the sample change, of course, right? Well, how else will S squared change? Then X bar will also change. But if S squared increases, does that mean that X bar have to increase too? Right? You see, this is where you got to get your math right, right? If LR is an increasing function of S squared, then fine, you got this piece, fine. But you have not controlled this piece. This is exactly different from what we've been doing before, where we throw away some irrelevant stuff. This is not irrelevant. Why not? Because is it part of the sample too, right? So basically anything that's part of the sample, you cannot ignore when you analyze the likelihood ratio, because, through the sample change, the likelihood ratio will change. So that means that if you really want to show that likelihood ratio is an increasing function of S squared, you better be able to control this piece also through S squared. Or in other words, we have not been successful in showing that likelihood ratio is only a function of S squared. Okay. Look at the other example, like the mean sample, right? You see that after you reduce this, it's only a function of X bar. The rest are constants. So the likelihood ratio only depends on through the sample, right? On the sample through X bar as a statistic. But here, the likelihood ratio depends on S squared and X bar together. Does that make sense? So because of this, you cannot say that likelihood ratio is an increasing function of S squared in this case. Do you understand? Right. So if you want, you can say this: S squared increase does not mean X bar will increase. S squared and X bar can move in two different directions. So if S squared increase and X bar decreases, that doesn't mean LR will increase. Okay. So what does that mean about C? What does that mean about this critical region? What does that mean about the critical region? Correct. So exactly, C may not be the most powerful region. And in fact, it may not be. So I hope this example kind of comes to show you that if sometimes, right, do not expect, right? Of course, most of the problems are quite routine. You do it, you check it, it works. But don't be, so automatic, right? Because there could be subtle points that you will make an error on if you just kind of automatically try to push through, right? Here, if you are honest and if you are very careful, no, it's not the most powerful. Or yeah, the proof doesn't work. Okay, Neyman Pearson does not apply. Any question here up to this point? Then we'll address, right, what's wrong with C. But is it okay? Any question? So maybe let me put on one more line here, right? LR also depends on X bar. Okay, so now let's revisit. So this is our sample. Oh, yeah, I mean, how to say this, right? I guess, for example, I mean, if you have something like this, right? And this is very, very trivial, but I just want to show you. Suppose I have a sample that's 1, 1, 1, 1. What's X bar and what's S square? Yeah, and S square is? Mm-hmm. Right. Again, it's very, very trivial, but you can generalize what I'm trying to do here. But then if I have this, then what's X bar? And S square is? Yeah. And you can subtract 1. So do you see the point? That if you move, right, the sample all to, horizontally, you will change X bar, but you won't mess around with S square. Is that okay? All right, sure. But yeah, it is very interesting point that exactly you want to understand this small stuff, right? To kind of get a feel of what the statistics doing. All right, so now let's go back to our setting. We have, right, the normal population where we say the mean is 0 and the variance is unknown, and we want to test. And we propose this is the rejection region, right? And then we see that this may not be the most powerful. So what's wrong with this? Wrong in the sense that why is it not most powerful? Does anyone have a clue on this? So let me give you a hint too, right? The hint is that this is a reduction step, right? Usually we just jump to the reduction step, right? By guessing the intuitive statistic. The full-fledged rejection region should be obtained through likelihood ratio. In other words, likelihood ratio is the one that will point to you what the most powerful one is. But of course, right, when we do the reduction work, if it lands on the statistic, then we're done. But here, right, look at this likelihood ratio. What does it kind of point to as the statistic to use? Right? What does it seem like the statistic to be used here is? Look at this. So, right, this is not true. But this is what we get from the likelihood ratio. What does it seem to tell you about the statistic to use? it seems to tell you that this is the right one to use, not S squared. So I'm not sure if you're surprised by that, but so can anyone propose another one that somehow is based on this? Well, it will be that. This is the critical region I want to use. And if I use this, then it will be the most powerful. Are you surprised? Do you have questions? Or do you see why this is the appropriate one to use here? Even intuitively. So to recap, right? The message is if I have x1 up to xn IID, normal 0 sigma square, and I want to do hypothesis test on the sample variance, then the rejection region that involve S square is not the most powerful, but is. Yeah, Alice. That's my question for you. What's the intuition? Well, okay, let me give you a hint. What is this trying to point to? Can you see this as an estimator? Or can you modify this to become an estimator of something? Can this be viewed as an estimator? Okay, so maybe that's a little bit hard. Let me ask you another question. This is strange because you never seen this before. But again, right, you got to be flexible and not just stay bounded to your. Yeah, that's pushing it too far. Yeah. Okay, so this is my question. Suppose I have this context. What is the best? Suppose I just ask you this question. What can you tell me? If I have IID normal sample, but the population mean is known, what is the best estimator for the population variance? S square? Correct. So what's the division here? By what? Correct. So you see that S square goes out of its way to estimate mu, which of course is appropriate when mu is unknown, right? But S square is not very efficient if you don't take into account the fact that mu is known. Because if you spend your effort estimating mu by x bar, you introduce more variation into here. So in other words, the variance of S square will be bigger than the variance of S prime square in this case. Now, of course, right, this is nonsense if mu is unknown, because how can that be an estimator? But if mu is known, that is perfectly legal. And if you want to squeeze things out, right, in terms of efficiency, this is the most efficient. All right. Just the way it works. So again, right, in our context, what are we saying? Mu is known. So what are we saying here? This, right, or rather, you see, the critical region where this is less than or equal to k, for example, right, is exactly the same as sum of xi squared over n is less than or equal to k over n. Or you can change that to some other number, k prime. So actually, right, the whole point of this critical region not being the most powerful is because you're not using the best estimator for sigma square. And right, the likelihood ratio kind of points you to that. It says that, watch out, you're not really using the right estimator here. So here, right, this is the one. Is that okay? Any question on this? Are we okay? So now, right, I hope that after you do this, then you can prove that C bar, right, I would say this, right, it is straightforward to show that C prime is the most powerful. Okay, so I'll leave some of these questions for you as quiz so you can explore. For example, right, is S prime biased or unbiased? By the way, right, it's not really the S prime that we're using before either, right? It's X bar. But anyway, I just use the same notation, not to introduce more stuff. Is this guy biased or unbiased? Should be unbiased. This guy should be more efficient than this, right? Again, I'll ask you to do a calculation to show that. And finally, right, once you propose this rejection region, then you can just reject it. Any question? So again, right, the moral of the question is that the likelihood ratio is a better tool, right, to do rejection than kind of aiming at things like this. All right, but of course, there are reasons why, right, we use this structure rather than the likelihood ratio. What's the reason? The reason, right, is that if you want to decide K, right, so that you want to decide the size of the rejection region, then the likelihood ratio is not a very friendly object to work with. So the reduction step, right, the reduction step to reduce the likelihood ratio to some dependence on a statistic that we know the distribution of. That's the point of reducing it to something like C, okay? But the object with the most information is the likelihood ratio. Any question? Too abstract? This example may be a little more subtle for you, right? But I think it brings home the whole kind of likelihood ratio stuff. So try to see where it is that you may still be struggling with the concept and ask the question, all right? So let me proceed to the next question, or next example. Suppose now I have x1 up to xn, IID, normal, mu, sigma square, both unknown. Both unknown, okay? And I want to do hypothesis tests on sigma. You know what? Let me change it to numbers. Maybe it helps. What critical region you think we should use? And how do we proceed with the likelihood ratio? So first of all, what critical region should we use here? No, Alice, this time you're too much into the other example. Here, mu is unknown. Oh, this is fine. This is fine, right? But again, that's why I say it's very subtle, right? This is probably why it's really annoying to do statistic, but small details like this can change everything. Correct. Here, S square actually is appropriate. Why? Because mu is unknown. Okay. So here, S square is bigger and bigger, right? Not less, because of the 4 and the 1. Okay. Can we use Neyman-Pearson to explore the power of C? Okay, I mean, frankly speaking, is C the most powerful is the question I am asking. Well, let's see. So I would do something like this, right? The likelihood ratio, which is, right, I don't know, 1 over square root of 2 pi sigma 0 square, which is 1, right? Raised to the n over 2, e to a minus 1/2 sum of xi minus mu square divided by 1 over square root of 2 pi times 4, right? Raised to n over 2, e to a minus 1/2 sum of xi minus mu square over 4. What do you mean they're both no, Christine? Oh, I apologize. It's just a typo. Yeah, H1, sorry. Yeah. Okay. So let me ask you this before we even try something. I guess, you know, here you probably think that we want to make S square show up, etc., right? Let me ask you this. Can we work with this likelihood ratio? In other words, right, please try not to think of likelihood ratio as a very abstract object. You can really compute it out as a number, right? And actually we can, and we do, right? Recall my simulation example with the binomials, right? The likelihood ratio is a number, okay? Is a number. It's just that before you do the experiment, you just think of it as, as a random object. But in other words, likelihood ratio is a statistic. So it should be known when you observe the sample. Okay. So let me ask you this. Is the likelihood ratio here something we can work with? Answer, no. Because mu is unknown. Correct. All right. So in fact, look at this. What kind of hypothesis is this? What kind of hypothesis is this? Simple or composite? All right, remember, right? So again, this is why words are also a little bit subtle. What does simple hypothesis mean? Simple, right? By the way, simple does not mean that something equal to something that is a simple hypothesis, right? What did I say about simple hypothesis? What does it mean? Yeah, simple hypothesis means the distribution is completely determined under the hypothesis, right? Meaning you can compute all probabilities. So here, even though it's stated like this, actually it's a composite hypothesis because mu is unknown. Or in other words, right? I mean, basically, the distribution is not completely determined under this hypothesis. You don't know what mu is. Is that okay? So in that setting, for that reason, this is not, Neyman-Pearson context does not apply here because you're not actually in simple hypothesis. Are you okay? So, right, I state this so that can be very, very kind of subtle to walk into this and say, yeah, that's Neyman-Pearson. No, this is not Neyman-Pearson because you're not in the simple hypothesis. Obviously, you want to replace this with X bar, right? You're just itching to do so, which I agree. That's a natural thing to do. But if you were to do that, are these likelihood ratio? If you replace it with X bar, are these likelihood ratio? The answer is no, right? Because, I mean, likelihood means the probability, the density function multiplying together. The density does not involve X bar to begin with. So when you plug in X bar right here, you're talking about some object that looks like likelihood ratio, but it's not. So it's called the generalized likelihood ratio. And that's going to be the topic of the next section. Okay. So yes, we will replace X bar here. But the emphasis is that Neyman-Pearson is no longer in the context. In other words, the power of C is something that should be left, undiscussed, or actually this is unknown. So are you okay? All right. So I hope like there are kind of 3 instructive examples for you. The first one is when mu is unknown, sigma is known. Then X bar, right, being the statistic of choice, will lead you to the most powerful one. The second case is when mu is known and sigma is unknown. In that case, S square, our usual friend, is not the statistic to be used because mu is known. So you have to use the sum of xi minus mu square, right, divided by n as the statistic. So both of those do fall under Neyman-Pearson. So basically, Neyman-Pearson is a hypothesis on, kind of like on one statistic, on one parameter, if you will, right? Or if you want to do two parameters, then they better both be known, all right? They both better be simple, right? So in other words, you probably have to do, but then mu is known. But when both of them are unknown, one of them is unknown, one of them is a hypothesis, then that's no longer Neyman-Pearson because the distribution is no longer completely determined. So there's three contexts, right? And how their relevance to Neyman-Pearson should be something you should try to understand, all right? And if you understand this, I think you get a hang of what the whole likelihood ratio business is doing. Any question? Okay. So moving on to 12.6 would be the likelihood ratio test. All right. And the point of this is to give you the most general approach to hypothesis testing. So this is the tool to come up with a generic rejection region in any hypothesis testing context. Okay. So the setup is this, and this can be very general. Suppose you have a null hypothesis where you say that your theta is in some region. And by this, I mean, right, it can be more than one parameter because I do a vector of theta. So it can be more than one parameter. The alternative is theta is in some other region. Okay. Now, all right, that's as vague as it sounds. But for example, right, the null is mu equal to 0, and the alternative mu is not equal to 0 falls into this context, right? Because the first region is just a point 0. The second is, right, everything but not 0. Some other one is just the one that we just looked at before. H0 sigma square, right, equals to 1. H1 sigma square is equal to, let's say, 4. So stated in this, it sounds like a simple hypothesis, but we kind of suppress the other, right? The other parameter, which is mu. So here, right, the explicit one would be sigma square equals to 1. Mu is just a real value. Sigma square equals to 4. mu just a real value, right? So in other words, because this is the case, we don't bother, right, spelling it out, but still, right, this is really the pair, right? The pair mu sigma square is in R, right, cross 1. The pair mu sigma square is in R cross 4, for example, in some region. All right. So the approach, right? So what is this, right? Of course, the question is how to come up with some rejection region. All right, I don't care. So first of all, right, I don't care what, how powerful it is or what size it is yet. I just want to have a structure to work with. Because, for example, this context may still be intuitive enough for you to guess some region by, kind of, how to say this, by using the estimator, right? So here you kind of intuitively go with X bar. Here you intuitively go with S square, right? You don't care. I mean, you don't want to go with all the theory. But when you do more advanced statistics, especially when the number of parameters grow and it's unclear what those parameters are doing, in some sort of model, some really strange model where the parameters are just like, controlling some aspects of the model, then it's unclear what estimator to be used for those models. So, having a uniform approach to obtaining a rejection region would be very valuable as your model gets more complex and the meaning of the parameters become less tractable. And actually the rejection region here is very, very intuitive. What is it? It's going to be something I would call a GLR, okay? GLR stands for generalized likelihood ratio. Because the emphasis is that it's not going to be a likelihood ratio because it's going to be the max over all scenario under the norm divided by the max under all scenario under the alternative. Okay. And that's it. So by the way, right, this is like your MLE context. Because when you try to, find an estimator for theta, right, you try to find the maximum likelihood. But here you maximize the likelihood function without, maybe you probably wouldn't really want to know what theta attains that value to. But here it's like maximum likelihood restricted to the norm. Maximum likelihood restricted to the alternative, for example. Okay. And the reason why this is not a likelihood ratio exactly because the top is not a likelihood function, right? The top is the maximum of likelihood function. The bottom is also not a likelihood function, but the maximum likelihood function. Okay. So what's our rejection region? Our rejection region is this. Reject when the general likelihood ratio is small enough. That's it. Oh, apologize. I think it's not under H1, under everything. Apologize. The bottom is the union. Yeah, sorry. It could be done under H1, doesn't matter, but actually under everything. Okay, so reject when the general likelihood ratio is less than or equal to K. And what's the intuition behind this rejection region? Or what we're saying is the critical region is when the generalized likelihood ratio is less than or equal to K. That's what we're saying. What's the intuition behind this? Again, well, you're weighing the evidence, right, under the norm against all the other scenarios. right? I mean, technically speaking, you are weighing under the alternative, but it doesn't hurt to throw everything in. So in other words, right, if the evidence under the no against everything else is small, that means the no is not likely to happen. And so you would go with the alternative. But if the evidence under no against everything else is high, then you would go with the no. So that's the intuition for the generalized likelihood ratio. Or, this whole procedure is called the likelihood ratio test. Is that okay? Any question? So let's look at examples. Suppose that I have x1 up to xn, IID, normal mu sigma square, right? Again, this is our go-to example. We have three cases. The first one, mu known, sigma square, sorry, mu unknown, sigma square equals to 1. Then the hypothesis that mu, let's say mu equals to 1, mu not equal to 1, for example, right, would be equal to, sorry, maybe let me do this, mu equals to 2, let's say, right? Then the likelihood ratio would be exactly what we have formed before, which is, e to the minus sum of xi minus 1 square over 2 divided by e to the minus sum of xi minus 2 square over 2. And this is a likelihood ratio because everything reduced down to 1 point. There's no maximum needs to be taken. There's no maximum needs to be taken, right? There's no maximum needs to be taken because everything is determined. The second scenario where mu is equal to 0, sigma square unknown, right? And our hypothesis is like sigma square equals to 4 and h1 sigma square equals to 1. Then the likelihood ratio is 1 over, right, square root of 2 pi times 4 raised to n over 2 e to the minus, right, sum of xi square over 2 times 4 divided by 1 over square root of 2 pi times 1 raised to n over 2 e to the minus sum of xi square over 2 times 1. Again, right, there's no maximum taken in A and B because everything is a 1 point, right? No, the hypothesis is truly simple in all of A and B. So in A and B, no maximization happen. Because the hypotheses are simple. Okay. C, let's say, mu sigma square both unknown. Okay. The known is sigma square is equal to 4. The alternative is sigma square is equal to 1. So in this case, because mu is unknown, right, we need to look at the generalized likelihood ratio, which is what? Which is max over all mu, right? And then sigma square equals to 4 of the likelihood ratio, right? Of the likelihood function, which is 1 over, right, square of 2 pi times 4 raised to n over 2 e to the minus, right, sum of xi minus mu square over 2 times 4 divided by the max over all mu, and sigma square equals to 1 of this. Is that okay? Any question on this? So again, right, this was just the 3 problems that we worked with before. But, you know, like, so this indeed is a generalized version of what we did before, because when, right, when there's nothing to maximize, then the generalized likelihood ratio reduced to just the likelihood ratio. But when there are truly, right, a unknown parameter where we need to maximize, then it indeed, right, will take on this structure. And it no longer is a likelihood ratio. And so our task, right, is to solve for the maximization problem in, right, H0 and H0 union H1, right? And B is to solve for K so that the rejection region of the form C equals to the generalized likelihood ratio less than or equal to K has size alpha. Okay. A is usually very easy because, you know, you just kind of do your MLE approach. For example, here, right, the maximum of this one will happen when this is x bar, when mu is equal to x bar. So you just actually plug in x bar here. The harder thing, right, in a lot of time is to, once you compute this generalized likelihood ratio, you do not know its distribution. You do not know its distribution. So that, right, deciding this little k so that the critical region has size alpha, right, is actually the challenging work. So in most cases, deciding the distribution of GLR, right, the generalized likelihood ratio, is the most challenging step. And may not be able to done, and may not be obtained in closed form. In other words, you know, except for some very special case like the normal example, a lot of time we have to do the asymptotic, where we have to let the sample size get large, and we say that the generalized likelihood ratio has some structure. Okay, and that's what we'll do. Okay, I think this is where I want to stop here. Do you have any questions? Yeah. Is it here that you want? I don't know where you want it. Here, maybe. Yeah, so there are still some students taking the makeup. And so that will happen on Monday. So your exam result will come out Monday afternoon, or sometime like that. Okay. Sure. All right. So thank you for attending, guys. I'll see you. And if you have questions, I'll try to answer. So, you know, I think these are not three cases where Neyman Pearson, I'm not sure if you get the number 3 from here. Neyman Pearson applies to both of these, right? Neyman Pearson applies to both of these. So Neyman Pearson does not apply in composite hypothesis, that's all. Whenever you have a true likelihood ratio, right? And you can do this and this, then Neyman Pearson does apply. So I don't see where the 1, 2, 3 comes from, right? It's just really simple versus composite, right? When I did this example, what I wanted to show you is when you try the reduction, when you do this, let's say, then your intuition is too quick. You're not quite looking at the likelihood ratio, because the likelihood ratio does not point you to S squared, but it points you to, you know, the other one, which is sum of xi minus mu over n, right? But both of these still falls under Neyman Pearson. Only the last one, because it's no longer likelihood ratio, that it does not fall under Neyman Pearson. Is that okay? Or do you have some other question? Yeah, so to recap, right? Whenever you have likelihood ratio, meaning simple hypothesis, you have Neyman Pearson. The whole point of Neyman Pearson, right? And the whole point that people may get it wrong is they may get the wrong reduction. Again, right? You see, this is where somehow our intuition wants to leap ahead, because you see sigma square, right? You got so trained that you say, okay, let's use S square. Okay, fine. I'm not saying this is not reasonable. This is reasonable. But exactly, Neyman Pearson would say that may not be the most powerful. That's all, right? But if you, so the whole message here, believe it or not, is that likelihood ratio is where you want to start. You do not want to start here. You know, you don't want to start here, actually. Let's see this. Because you may or may not end up with it using likelihood ratio. So likelihood ratio is a more robust object to start using. Of course, the point is likelihood ratio is too complex, right, in terms of its distribution. So you want to reduce it down to this. But in terms of power and everything appropriately, you know, like for the test, this is you know, something to start with. Same thing here, right? Even down to here, this is still something to start with. But you see, it gets more and more complex as you get, you know, your hypothesis gets more and more composite, for example. Yeah. All right. Any other question? You too. Thanks. Thank you.